Welcome to Scale Up University. Welcome to Probability for Machine Learning course. So this is the module 2, lecture 2. So this is the lecture number 2 of module 2. That is why uncertainty exists in machine learning systems. Now, before moving forward, let us first discuss one very important misconception with regards to machine learning, that if we collect enough data and use a powerful algorithm, predictions should become certain. So the idea is, with huge training data, with state of the art algorithms, and with very good computational power, we can make highly accurate machine learning systems. So it is wrong. Why it is wrong? Because despite of you training the model with huge data, despite you using state of the art algorithms and state of the art computational resources like GPUs, still there are certain inputs which will definitely give wrong answers. And the main reason for that is the training data is a sample of reality. The collection of all the possible data for the training is the population. And no matter how large training data you take, that will always be a subset of that population. That will always be a sample of reality. So there will always be certain patterns which we will be missing while we will be training our models. And one more very important factor is the noise. No matter how cautious you are while preparing the data, while pre-processing the data, noise is something which we cannot avoid fully. Noise will be there, and because of that noise, accuracy will suffer. Like predictions will become a sort of uncertain. So certainty we cannot achieve. So this misconception is very clear to us, and that is what is this lecture is about. Why uncertainty exists in machine learning systems. So in this lecture, we will get a very good clarity on this. Like despite you using lots of training data, huge training data, petabytes of training data, despite you using state of the art algorithms, and despite you using powerful computational resources, despite of all of that, uncertainty will exist in machine learning systems. So uncertainty is something which is inherent, which is like the property of a machine learning system. Uncertainty is not a bug, it's not a shortcoming, but it's a it's something formal, it's something inherent, it's something the property of machine learning system. So that is what we will learn in this lecture. So if we look at the topics that we will discuss in this lecture, so first we will be talking about why is perfect prediction impossible. Then we will be discussing real world data versus idealized data. Then we will talk about incompleteness of observations. Then we will be talking about why uncertainty persists even with large data sets. Like if we make use of huge data sets, then also uncertainty will be there. Why better algorithms do not remove uncertainty. And we will conclude this lecture by discussing what does this mean for machine learning design. So it will be a very interesting lecture wherein we will be discussing why uncertainty is inherent in machine learning systems. So all these topics we will discuss one by one. So this is the lecture number 2 of module 2. Module 2 is uncertainty in machine learning, and this lecture 2 is why uncertainty exists in machine learning systems. So we will start with the first topic, that is why is perfect prediction impossible. Now if you talk about perfect prediction, it would require complete information. Complete information means when we are training the model, we should be training it with a population, like all the possible data points of training should be considered. So perfect prediction would require complete information. It would require zero noise. It would require a static word where data is not changing. And it would require deterministic relationships. Now, unfortunately, If we talk about machine learning systems, none of these exist in real machine learning problems. Now, this uncertainty, it is not about poor engineering. Uncertainty is not about our poor engineering. It means it's not about the model. It's not about the shortcomings in the model. Rather, it's about it is due to limits of knowledge. And now I hope this limits of knowledge is clear to you, that we are just partially observing the reality. We are taking into consideration the sample of reality and not the actual reality. The machine learning model is seeing, it is getting trained on the sample of reality. It is partially observing the reality. So that's the limits of knowledge we are talking about. So now it's very clear to you that why perfect prediction is impossible, because machine learning problems, real world machine learning problems, they deal with systems, they deal with data which is a partial observation of the actual reality, which contains noise, which is highly dynamic. Their overlapping relationship is there, which is highly stochastic in nature. And uncertainty is not about the shortcomings in the algorithms or shortcomings in the model, but it's due to limits of knowledge. If we talk about a real world example of stock price prediction, so in stock price prediction, what happens is model predicts tomorrow's stock price. So that is stock price prediction. The model predicts tomorrow's stock price. Now, what's the problem with this model is that despite you train it with huge data set, using state-of-the-art algorithms, using powerful computational resources, there will always be some news which may break overnight. And this news might cause a disruption. Like whatever your model, like the patterns it learned, whatever the training it did, it might whatever predictions it will make, it will be very different from the actual reality, because the news, while you trained your model, you haven't considered the news. So news may break overnight, and this news may disrupt the real world system. So here we are talking about the static world. So the real world which we live in is highly dynamic in nature, and this dynamic world may cause problem. And here the problem is very clear to you, because based on the patterns, your model will be predicting something which should be very close to reality, but some events of the real world, it deviated the price to a totally different level, and hence this is the dynamic world we live in, and the predictions, it goes wrong, and it introduces very high level of uncertainty. Some rumors or human emotions may shift markets. Random events dominate short-term movement. So this is the idea. So here what is happening is that the world we live in is dynamic. So what we can say, like one very important observation we have to make. So here the model failed, not because it was weak. So models don't fail because they are weak. Like the failure of model is not because of model, but because they fail, models fail because the future is hidden, and future is hidden means incomplete information, dynamic word, because the model has not seen those patterns, model has not seen those kinds of behavior. Because of that, the model may fail. So we can conclude this topic by saying that if we talk about perfect prediction, like if we want to have perfect prediction, it would require perfect foresight, and that is not possible in the real world, because the real world is stochastic in nature. The real world is highly uncertain. We don't know what future is. So since we cannot have the perfect foresight, we cannot have perfect predictions. So now it's very clear, and hence we say that perfect prediction is impossible. We are using the word impossible. And now it's very clear to you why it is impossible. Okay, now we look into the next topic of this lecture, that is real world data versus idealized data. So we can make two columns, idealized data versus real world data. Now see, idealized data has to be clean, it has to be complete because it's ideal, no noise. It has to be fully complete, noise free, and perfectly labeled. But if we talk about real world data, it has missing values. It cannot be clean. It has missing values in it. Like it can have missing values. Like if we talk about completeness, real world data is always a sample of reality. It will always be a partial observation of actual reality. So it can have biases and imbalance. If I talk about real world data, it can have noisy measurements and it can have incorrect labeling. Because in real world data, we cannot expect perfectly labeled. Incorrect labels might exist, human errors or some other error. Data will be having some noise. Data will be incomplete. It might have bias and imbalances also. It might contain missing values. Now, for example, if we talk about image data set, if we take a real world example, now the training images, now the training images are well lit, centered, and high resolution. Like in the image data set, for training the model, we used as a sort of idealized data wherein we trained the model using well lit images, centered images, high resolution images. But when it comes to production, like when the model is deployed and when it is given the real images, we call it the production images. And unfortunately, those images, like some of them might be dark, some of them might be blurry, occluded, and also images taken from different angles. And because of that, no matter how good the model was performing while training or while evaluation, because see, when you are evaluating the model, what you are doing, whatever training images you collected, 30% of it you will be using it for testing and validation purpose, and 70% you will be using for training purpose. So you will be training the model, evaluating the model using ideal images like well lit, centered, high resolution. But when that model is exposed to the real world, then that model will not perform because the real world data is very much different from idealized data, and it's a perfect example. So we can say that data uncertainty is baked in at the collection stage or data set preparation stage, because when you are collecting the data, when you're preparing the data, then only data uncertainty will come into picture. Because when you will be collecting the real world data, that data will have some noise, noisy measurements, missing values, biasness, imbalanceness, incorrect labels. And unfortunately, the real world data is very much different from ideal data. So in the lab, you may make use of ideal data. Like here we saw, we trained the model using ideal data with very less uncertainty. And there you might get magical accuracy. But when that same model is exposed to the real world, when it is deployed to the production, the same model will start, like it will start underperforming. Like the accuracy will suffer a lot. And now the idea is very clear because the real world data is having uncertainty in it. And now it's very clear the difference between real world data and idealized data. Okay, now we'll look at the next topic of this lecture, that is incompleteness of observations. So if we talk about machine learning systems, they observe proxies, not reality. Like machine learning systems, they observe proxies, not reality. Means they observe partial reality. Machine learning systems, they see features, not causes. So we can say that machine learning systems never observe true intent. because since it is observing the partial reality, it is not able to observe the true intent. It's not able to observe the hidden variables. It's not able to observe the all influencing factors. So machine learning systems, they observe partial reality, sample of population, partial reality. So they are observing proxies and not the actual reality. They see features, not causes. And what is the difference between that? Features means some of the attributes, and causes means the features which are influencing the target variables. Since machine learning systems, they deal with incomplete information. So there is a high chance that they will miss out many of the influencing factors. So machine learning systems, they never observe all the influencing factors. That is one very big problem with machine learning systems because the knowledge is limited. It deals with the limited knowledge because the training is always done on the partial reality. So all influencing factors are not considered. There are many hidden variables that might influence the target, and that is not taken into consideration. And hence, machine learning systems never observe true intent, and that is what is incompleteness of observations is. And this creates uncertainty. Incompleteness of observations creates uncertainty. If we take a real world example, that is loan approval. So let us suppose we observed income, like the machine learning model we are making, it is taking into consideration the income, the credit score, and the employment history. And let us suppose it missed certain critical features like future job loss, like what's the chance that or job security, you can say that, future job loss, health emergencies, and personal decisions. Now see what is happening here. Let us suppose I made a machine learning model which will approve the loan, and to approve the loan it is taking into consideration only three features: income, credit score, and employment history. Now let us suppose two applicants with the same income, same credit score, and same employment history were given loan. Now one did the repayment, but the other got default. Like he was not able to repay the loan. Now that's the problem because with the same identical input feature but different outcomes. But if we also include all the influencing factor, because here what the problem was, why the same or the identical input created different outputs, and the model was not that good because we got loan defaults. Ideal model will be the one which will be giving loan to only those applicants which will always repay. So problem was we did not consider all the influencing factors. There were certain hidden variables like the job security, health emergencies, and personal decisions. And because since we missed these like influencing factors, so we can say that unobserved variables, it guarantees uncertainty. Unobserved variables, it guarantee uncertainty because it is making sense. Because see, the idea is that the more the unobserved variables you are having, the more the uncertain outcome will be because clarity is missing. All the influencing factors are not taken into consideration. So the model, it will give like suspicious outputs, like it might give loan to less deserving candidates, less deserving applicants, it can give loan to them. But if all the influencing factors are taken into consideration, this uncertainty will like it will reduce, and model will be like it will become more strict in giving loans, and that is what is needed. And hence in the real world, the machine learning systems which you will be building, hundreds of features, hundreds of influencing factors, or even thousands of influencing factors are taken into consideration, because then the model will be more strict in taking decisions, and that is what is needed. So now it is very clear to us incompleteness of observations. Incompleteness of observations means while training the model, if we ignore important variables, if we don't consider influencing factors properly, then that will be incompleteness of observation, and definitely that will basically reduce the accuracy of the model, because the model will be giving wrong predictions. Now we will discuss the next topic of this lecture, that is why uncertainty persists even with large data sets. Now there is a myth in machine learning or in like artificial intelligence in general. More data fixes everything. So it's a myth. More data fixes everything. So the idea is that despite of you having huge data sets, uncertainty will still be there. And why is it so? That is what we will discuss now. Now see, if I talk about more data, so more data helps, but it does not reveal hidden variables. It does not remove randomness. It does not stop the word from changing. So the idea is that despite you are having huge data sets, it will not reveal hidden variables. Because see, having huge data sets means you have taken a vector with, let us suppose, 100 features, and now you are just increasing the number of samples of it. Like earlier, let us suppose you had 1,000 samples, now you are having 10,000 samples, but the feature is same, like 100 features you are taking into consideration. So more data is not revealing hidden variables. More data does not remove randomness, because there might be noise in the data. So more data you will be like, as you will be increasing the size of the data, the randomness will increase, the noise, the probability of noise will increase, and it will not remove randomness. And uh, one more very interesting thing, like we live in a dynamic world. So despite you are having huge data, the word might change, because the events might create some sort of uncertainties that might affect the model in a negative way. Like we saw the example of stock price prediction, wherein let us suppose you used petabytes of data to train the model and you made a state of the art model. But because of some event, some news, the actual price will be far away from your prediction, and your model will just end up giving wrong predictions. So here, huge data did not played a role. It did not help us. So with the more data, so with more data, some uncertainty will definitely shrink. So with more data, uncertainty shrinks, but it will never disappear. Some uncertainty never disappears. So that is the idea. If we talk about weather forecasting example, like a real world example, we are talking about weather forecasting. So weather models, they make use of massive data sets. Weather models, they make use of powerful simulations. Despite of that, long-term forecast, it remain uncertain. So weather models make use of massive data sets. Weather models make use of powerful simulations. Despite of that, long-term forecast remain uncertain. So we can say that uncertainty has irreducible components, meaning to say that there are certain uncertainty which we cannot remove. So uncertainty has certain components which are irreducible, which cannot be reduced, which cannot be removed, which cannot be disappeared. That's the idea. So now it's very clear that why uncertainty persists even with large data sets, because if you keep on increasing the size of the data set, it does not mean that you are revealing the you are taking into consideration all the influencing factor. It is not like that. You might be introducing more and more noise, randomness, and increasing the data set, like increasing the size of the data set, will not make it prone to external events, because the real world is changing rapidly, and external events will definitely have an influence, and that we cannot take into consideration. So with more data, some uncertainty you can shrink, but there are some uncertainty. Uncertainty has some irreducible components which will never disappear. Okay, now we will look at the next topic of this lecture. Why better algorithms do not remove uncertainty. Now we will talk about one illusion, the algorithmic illusion. Now this algorithm illusion, it talks about if we just use deep learning, uncertainty will go away. If we just use deep learning, uncertainty will go away. It's an illusion. Why it's an illusion? Let us look at that. If we talk about the reality, see, algorithms learn patterns. Whether it's a machine learning algorithm or a deep learning algorithms, they learn patterns. And algorithms do not change the data generation process. Algorithms do not change the data generation process. So this is a very important point I am discussing. See, we have been telling this uh, in like many of the previous lectures also, that uncertainty is not about shortcomings in the algorithm or shortcomings in the model, but it is mainly because of the data. So data is introducing uncertainty and not the algorithm. So if we say that if we use deep learning, then uncertainty will go away, it's a wrong statement. And now I think it is making sense to you why it is wrong. Because uncertainty has very little, or you can say that uncertainty has nothing to do with algorithm or the model. Uncertainty mainly has to do with the data. So the reality is that algorithms learn patterns. So whatever data you will feed, it will learn it. So the data, so data generation process. So algorithm has nothing to do with the data generation process. Algorithm says that, okay, whatever you will feed me, I will learn accordingly. So this data generation process, it is responsible for uncertainty, because if the data is like, it is having lots of unobserved variables, like if it is not covering a good amount of reality, if the training data is not covering a good amount of actual reality, if many of the influencing factors are missing, then obviously the data will be having a very high level of uncertainty. And no matter state of the art algorithm you use, no matter if you use deep learning also, it will suffer, because whatever you're feeding, it will give predictions based on that only. So now I think it is very, very clear to you that why better algorithms do not remove uncertainty, because uncertainty is something which has to do with the data and not the algorithm or the model itself. So here one very interesting discussion we can make. We can talk about model improvements versus word uncertainty. Now, if we talk about better algorithms, like model improvement means better algorithms. So better algorithms, they can reduce the bias, they can improve approximation, but better algorithms, they cannot, or they do not. Like, see, if you use better algorithms, if you improve the models, you will be able to reduce the bias, you will be able to improve the approximation, but better models, they do not eliminate noise, because they cannot eliminate noise in the data. Better models, they cannot, or they do not eliminate. They can, it might be that we don't know, we are not aware of the techniques. Techniques might exist which might enable the algorithms, the models, to eliminate noise. That might be the scenario. But in the current scenario, like models, they do not eliminate noise. In the current scenario, whatever models you are using, like the machine learning models, they do not observe the future, because the future is hidden from them. They do not observe the future, and like they do not reveal hidden variables. Now, here one very interesting thing I want to discuss with you. See, you might be aware of that, a very interesting fact, that in deep learning, there is no need for you to do feature engineering explicitly. Like whatever training data you are providing, deep learning model will learn the features on their own. But in machine learning, we have to do the feature engineering. I think this difference is very clear to you. Like in machine learning, we have to explicitly do the feature engineering, and we have to identify the features and give it to the model. But in deep learning, you just give it the data, it will do the feature engineering on its own. Like every layer will learn new features. But one very interesting thing, if the training data you are taking, if it is not taking into consideration lot of influencing factors, if lots of influencing factors are missing in that data, then deep learning will also suffer. Because whatever feature engineering deep learning will do on its own, it will be doing on the training data which you will provide. So if the training data which you are providing, if it is very much incomplete, if it is not taking into consideration all the influencing factors, then definitely the model will suffer. So that's why we are very so confidently we are saying that despite you improve the model, like from machine learning model you take to deep learning model, then also that deep learning model will not be revealing the hidden variables. Because what deep learning model can do is whatever training data you are passing, with that scope of information, it will identify the features and other influencing factors which is missing from the training data. Deep learning will never be able to understand that. So now it's very clear to us that despite you use state of the art algorithms, like why better algorithms do not remove uncertainty, because uncertainty has to do with the data and not with the models, not with the algorithms. Okay, now we'll discuss the last topic of this lecture, that is what does this means for ML design. Like whatever we discussed in this lecture, like why uncertainty exists in the machine learning system, what it means for machine learning design. So now it's very much clear that one should stop chasing certainty. So when you are building machine learning systems, so this should be very clear to you that stop chasing certainty and rather start designing for uncertainty. See, we already saw certainty leads to overfitting, certainty leads to overconfidence, and certainty leads to unsafe automation. Because see, the idea is that when the data will be having a very less uncertainty, like when the uh, models will be more certain, like when the randomness will be less in the data, then what will happen is that in the training or in the evaluation in the lab, it will perform, like it will give magical accuracy, we call it overfitting. But in the production, when that model is exposed to the real world, and that real world data, inherently it will have uncertainty, and in that scenario the model will suffer accuracy. So certainty will lead to overfitting, certainty will lead to overconfidence, because the accuracy will be so high that model will be giving predictions with 99% confidence, and it will lead to unsafe automation because the decision will be like unreliable. And we should start designing for uncertainty, because if we do so, so good ML systems, so good machine learning systems, if we talk about, they take into consideration output probabilities, and not just probabilities like the probability of the prediction, but also they expose the confidence, like whatever prediction they are making, what is the confidence level of that. Like let us suppose probability of occurrence of an event is 70% with the confidence of 80%. So good ML systems should output probabilities, they should expose confidence, and they should adapt behavior based on uncertainty. So if we talk about one real example, like fraud detection system. So here, instead of telling yes or no, we should give probability of fraud. Like we should not be certain that okay, fraud is like okay, it's a fraud or it's a not fraud. Rather, we should give probability of the fraud, probability of fraud. Rather, we should give probability of fraud, and also we should enable different actions based on risk level. So with this, like one very important point I will share with you. Uncertainty aware systems, like the systems which measure, manage, and make use of uncertainty aware systems, they outperform confident ones. So, in a real world, which is highly stochastic in nature, uncertainty aware systems will give you much reliable output as compared to confident ones. And this is like a very important point. And like we are concluding the lecture with this point: uncertainty aware systems outperform confident ones. So, finally, we completed this lecture. So, in this lecture, we saw that we should stop expecting perfect predictions, why perfect predictions are impossible. Then we also saw why uncertainty is unavoidable. No matter if you use huge data sets, large data sets, if you use state of the art algorithms, then also uncertainty is something which you cannot eliminate. We cannot get rid of uncertainty. That very good discussion we did. Then we also saw that the output of ML systems should always be probability. We should not say anything with full confidence or full certainty. Rather, it should be probabilistic output, and certain thresholds should be there based on which we can take actions. So, uncertainty is something which is inherent in machine learning systems. It is structural and it's not a bug, it's not accidental. So, I hope you enjoyed this lecture. You got some good understanding, some good clarity. So, do subscribe to our YouTube channel, Scale Up University, for more such interesting lectures and courses. And do share this lecture with your friends. Thanks for watching. Thanks for your time.